Okay, everyone, welcome to the third section of Chapter 5. In this section, we're going to discuss the issue of measurement error. So this is when either the independent variable or the dependent variable is measured with some sort of error. So measurement error occurs when a variable is measured inaccurately. We can apply our omitted variable bias concepts to help us understand the way in which measurement error affects our beta 1 hat estimates. OLS does well if measurement error is only on the dependent variable. All right, so if you have a dependent variable like, say, income or wages or weight or any of the ones that we've talked about through the semester, and it's measured with some sort of error, then it's usually not too big of a deal, especially if you have a relatively large data set. The measurement error there becomes a part of the overall error term. Now, it does increase your standard errors, which means it's harder to reject the null. So in a way, you can think of it as widening the hypothetical distribution of beta 1 hat. But overall, it's accounted for in the model. But if your measurement error is on your independent variable, especially your independent variable of interest, then you can have a problem. And the bottom line on this, and I'm going to walk you through why this happens, but the bottom line is that measurement error on the independent variable of interest causes the estimate to systematically be too small. It causes it to be attenuated. In other words, it pushes it towards zero. All right. So if the real effect should have been -5, you're going to get something closer to 0, closer to -4, -2 or something. And if the real effect should have been +5, it's going to push the estimate that you get towards 0, so to 3, to 2, to 1. So we call this an attenuation bias because it doesn't push it necessarily negative or positive, it pushes it towards 0. All right. And we're going to see why in this screencast. So let's suppose our true model is this. So we have a bivariate regression with x1 star, and we want to know what the effect of x1 star is on y. And what the star means here is this is the real variable I want, but we can't observe it directly for whatever reason. We don't have a perfect, precise measure of that variable. All right. We don't observe x1 star. What we can observe, though, is this other x1. All right, so this other x1 is an observable, probably correlated highly with the true x1 star, but it's something we can observe. We can see it. We can measure it. We can put it in our data set. All right. But x1 without the star measures x1 star with some sort of error. All right. So it's not exactly the same, but it is correlated, but with an error. So x1, the thing we can observe, measures x1 star, but with an error. And we're going to call this error term nu sub I here. So to isolate the problem of measurement error, let's assume we don't have any other types of problems. So we're going to assume that we don't have omitted variable bias. We don't have any of the other issues we've talked about. We don't have heteroscedasticity. All we have is just measurement error because we don't want to confuse all of those different problems. We don't want to confuse the effect of all those different problems. We want to isolate each one. So when we talked about heteroscedasticity, we assumed we were unbiased. When we talked about bias, we assumed we didn't have heteroscedasticity. In this situation, we're going to have measurement error, and we're going to assume we don't have heteroscedasticity and we don't have omitted variable bias or endogeneity. Now, in the real world, though, you can face all of these problems at once. But while we're getting our sea legs here, while we're figuring out exactly what the effect of measurement error is, we're going to assume no bias and no heteroscedasticity. All right. So let's assume we're talking about random measurement error. So this is measurement error that is not correlated with the value of x1 star. So it's not that when people are really, let's pick an example here. Let's say we're trying to measure wealth, all right? And we don't have wealth, but what we have is income, right? Income is correlated with wealth, but it's not wealth. So random measurement error would mean that we are mismeasuring wealth by using income for both rich people and poor people, right? The measurement error would not be correlated with X1 star. So income and wealth, that's probably not a good example of random measurement error. But what we're assuming for this example is that this error term is not correlated with the value of X, all right? So if we were somehow measuring people's heights, whatever measure we actually have of their height wouldn't be more wrong for tall people than short people, right? It's a random error, all right? So we would expect that the mean of all the individual errors then to be 0, right? If sometimes it measures people too high, sometimes the measure is too low, but on the whole it's random, we would expect overall that there wouldn't be systematic error, all right? So the mean of the distribution of the individual errors would be 0, all right? And so that seems like, oh, well, that's a great situation, right? Because I shouldn't have to worry about it. But that's the rub. If that random error is on your independent variable, it does cause a problem for us, all right? The measurement error for a given observation has no systematic relationship with the value of X1 that we observe. So for example, low values of X1 don't have higher measurement error or vice versa. So let's also assume we don't have omitted variable bias, as we just talked about. So E is the real error term, not the error term on the measurement, but the real error term in the model is not correlated with X1. All right, and so just to remind you, this is the error term in the model. This is everything correlated with Y that is not X1 star, and this is the error term in terms of the correlation between X and X1. How related are they? All right, so we don't have omitted variable bias. The error term is not correlated with X1 star. So we can use this expression for measurement error and insert that into the regression to see what effect having the ability to measure this one, but not this one, would do, what that would do to our estimate of beta 1. So the first thing we're going to need to do is solve for X1 star. So that's what I'm doing right here. I'm solving this expression for the fact that I can observe X1. I can't observe X1 star, but X1 is a measure of X1 star, but just with random error. All right, so I'm going to solve that for X1 star so I can use it in the next step. All right, what I'm going to do is I'm going to take the true model, all right, and I'm going to plug in this. I'm going to plug in what I can actually measure, but with error. So that's what I'm doing down here. I take this original, the true model. Oh, sorry, this doesn't want to highlight the way I want to, but I can take the true model here, and I'm going to substitute in for X1 star. And that's what I've done right here. All right, I've just substituted in this thing I can measure and the error term, all right, for the measurement. The error term for the measurement is new. And then I'm going to just multiply through. So beta 1 times X1 is beta 1 X1 I, and then beta 1 times negative nu is negative beta 1 nu. All right, don't forget to multiply it out correctly and get the negative term there. So this is what the regression would look like that I can run. All right. So we already know how to think about this problem though, right? What if I don't account for the measurement error? Well, that would be like leaving out a nu, right? That would be like leaving out a variable, and we kind of have a way of thinking about what happens when we leave out a variable we need. It's like an omitted variable, right? Because we don't observe this. So this would not be in the model. We can observe this, but we can't observe the random error because we don't know what the true X1 star is. It's not exactly the same as classic omitted variable bias. Omitted variable bias involves leaving out a variable correlated with both X and Y, all right? In this situation, it's not correlated with both X and Y, the error. The error is only correlated with X, but it's still going to have a problem, all right? We saw a classic omitted variable bias in the last screencast. It was this, and the bias was this, right? The bias was if both of these, if both of these are non-zero. If beta 2 is not 0 and delta 1 is not 0, beta 2 is the correlation between the omitted x2 and y, and delta 1 is the correlation between the omitted x2 and the included x1, right? That was the omitted variable problem, right? And we saw that depending on the sign of beta 2 and beta 1, the overall bias could be positive or negative. There's no beta 2 or delta 1 here. It's just nu, all right? An estimate of beta 1 hat will not equal beta 1 because v is a component of beta 1, right? Notice beta 1 here, the estimate is going to have it's going to be estimating both the effect of x1, the thing we can measure, and the measurement error. Measurement error will cause our estimates of beta 1 hat to be systematically wrong, but they are biased not in either positively or negatively, they are biased in one particular direction. And to see that, let's look at this PLEM, the probability limit of the distribution of beta 1 hat. So here's the PLEM. You can look back, we did this way back in section 3.5. This is the probability limit of the beta 1 hat distribution. And what we did is we wanted to say as n goes to infinity, what happens to beta 1 hat? And we had this expression, all right? So recall that sigma squared of anything is just the standard deviation. It's a measure of how spread out something is. So this is how spread out is x1 star. This is how spread out is x1 star. And this is how spread out is the error on the measurement of x1 star, right? Nu is the random error in terms of how well does x1 measure x1 star, all right? So we would have no measurement error problem if the probability limit of beta 1 hat equaled beta 1, right? That's what we want. So when would that be true? Well, notice that's true here when this is non-zero. If this is 0, then we just have this term over this term, and that's just a 1, right? So the variance around the error on x1 is the measurement error, all right? So the variance of the measurement error, if it's high, then we're going to have a problem, all right? So imagine if the measurement error for each person nu is a variable in the data set, all right? This would be the variance of that variable, right? Sigma squared x1 star is the variance of x1. Sigma squared v star is the variance of the measurement error. To understand what this tells us, let's look at some extreme values, all right? So what if there's no variance on the error term? Basically, there's no error. X1 measures x1 star perfectly, right? That means the nu would be 0 for everyone. It measures everyone's measurement. It measures everyone's x1 star perfectly. Well, if I plug that in, 0 variance, notice I just get that beta 1 hat, the probability limit of beta 1 hat equals beta 1. There's no problem. No measurement error means we get a good estimate. Let's consider where measurement error has a very large variance. Let's consider an infinity of the variance of the error term. So when I measure someone, it's a random error. When I measure someone's x1 star, it's random, but I could be all over the place. I could mismeasure them really low or really high. So what would that do to this value? Well, it would make the denominator here really, really, really big, which makes this overall fraction really, really, really small. So the probability limit of beta 1 hat would be beta 1 times a really, really, really small number. Mathematically, we know that beta 1 times a really small number is going to be less than beta 1, right? A really small number is less than 1, right? A number times a number less than 1 is less than the number itself, right? So beta 1 times 1/2 is less than beta 1. Beta 1 times 1/1000th is less than beta 1. Beta 1 times 1/1,000,000th is less than beta 1, right? So subbing into the second equation here, we see that beta 1 hat equals beta 1 times a really small number. So the probability limit of beta 1 hat is less than beta 1, all right? So the bottom line is high measurement error means we can't know the true effect of the variable x1 star's effect on y because our beta 1 hat distribution is no longer centered on beta 1. The probability limit of beta 1 hat is not beta 1. That's one of the things it means to be unbiased. We called it consistency, all right? So now we have an inconsistent measure of beta 1, all right? Beta 1 hat is biased, and it's going to be shifted toward 0. It's going to be attenuated. So when x1i is measured with error, x1i star, sorry, that needs a star. Oh, here we go. When x1i star is measured with error as x1, then beta 1 hat is going to have a value that is of a smaller magnitude than it should be. Right? It's going to be attenuated towards 0. All right? And this happens because the measurement error is sort of like an omitted variable from the estimated model. This form of bias is called attenuation bias. The beta 1 hat is closer to 0 than the true beta 1. All right, that is it for this one, and we will pick up the next one.